Welcome back to Very Ordinary Differential Equations. In this lecture, we learn about second-order Euler equations. Well, what is a second-order Euler equation? Well, the second-order linear homogeneous differential equation, x squared y double prime plus some constant xy prime plus some constant y equals 0 is called a second-order Euler equation. Now, there are two frequently presented techniques for how to solve this sort of differential equation, and we're actually going to go over both of them. The first method is to assume that the solution y is a power function, x to some power alpha, and then you try to solve for which alphas will solve that. Alternately, we can make a substitution of x equals e to the t and change our variables, and that will change this into an equation with constant coefficients, and we already know how to solve those. So let's go over how assuming y is a power of x can solve this second-order Euler equation. Now observe, every time we take a derivative of y, we multiply by a higher power of x. So y itself is multiplied by the constant b, y prime is multiplied by 1 power of x, and y double prime is multiplied by x squared. Now if y is a power of x, x to the alpha, every time you take a derivative, that will reduce the power by 1, but in our differential equation, we are multiplying by a correspondingly higher power of x. So for example, if you take two derivatives, assuming y is x to the alpha, you'll get alpha times alpha minus 1 times x to the alpha minus 2. But since we're multiplying this by x squared, this returns it to x to the alpha. One derivative of y would have been alpha times x to the alpha minus 1, but since we're multiplying by an x, this returns it to x to the alpha, and y started as a power of alpha. So all of these have a corresponding factor of x to the alpha. So then we can take our differential equation and plug these in. All terms have x to the alpha, which we just factor out, and we get alpha times alpha minus 1 plus a alpha plus b, all in parentheses, times x to the alpha must be 0. Okay, so having assumed that y is x to the alpha, we've changed our differential equation into this expression right here. Now, if I collect by corresponding powers of alpha itself, inside that parenthesis we get alpha squared plus a minus 1 times alpha plus b times x to the alpha is 0. Now, we want this to be true for every x in some interval on which we're finding our solution, and x to the alpha is not going to be 0 except at one particular point, x equals 0. Therefore, that quadratic expression in alpha must be 0. So having assumed that y is x to the alpha, we've taken that in our second-order Euler equation, x squared y double prime plus axy prime plus by equals 0, and determined that alpha squared plus a minus 1 alpha plus b must be equal to 0. But correspondingly, any alpha which solves this quadratic expression, alpha squared plus a minus 1 alpha plus b equals 0, will then generate an x to the alpha which solves the second-order Euler equation. So can we determine which alphas satisfy alpha squared plus a minus 1 alpha plus b equals 0? Yes, we definitely can. Capital A minus 1 and b are just constants, so we have a quadratic expression. We can use the quadratic formula. We'll get alpha is 1 minus a plus or minus a minus 1 squared minus 4b over 2. It's worth discussing why we have a 1 minus a here and an a minus 1 there. The coefficient in front of alpha is a minus 1. And in the quadratic formula, you would take negative 1 times this and stick it right here in the numerator of this fraction. But negative 1 times a minus 1, I've simply distributed the minus 1 and called that 1 minus a. In my opinion, it's a slightly cleaner presentation, and with fewer negative signs floating around, people are less likely to make a mistake when copying or using it. Now, if there are two distinct real numbers, alpha 1 and alpha 2, that the quadratic formula spits out here, well then we've found x to the alpha 1 and x to the alpha 2 are two distinct solutions to the second-order Euler equation. But as long as those powers are different, they will be linearly independent from one another, and therefore we found a fundamental set of solutions. But x to the alpha might not exist or be continuous when x is less than or equal to 0, depending on what that power alpha is. For example, suppose alpha is 1/2. In other words, we're taking the square root of x. Well then, when x is negative, that won't exist as a real valued function. So depending on what we find alpha to be, our solutions might not exist for all real numbers. We may have to restrict ourselves to the positive ones. So we've reduced the entire problem to a quadratic formula application giving us alpha should be 1 minus a plus or minus the square root of a minus 1 squared minus 4b over 2. And when there were two distinct real alphas that this produces, we know what to do. What if there's a single real alpha? In other words, that discriminant a minus 1 squared minus 4b is 0. Well, in this case, a fundamental set of solutions is given by x to the alpha and x to the alpha times the natural log of x. What if there's a pair of complex conjugate roots, alpha equals lambda plus or minus omega I? Well, then a fundamental set of solutions is given by x to the lambda times the cosine of omega log x and x to the lambda times the sine of omega log x. Now, in each of these possible cases, you can take this proposed fundamental set of solutions and manually check that they do solve the differential equation and that they are linearly independent. So overall, we assumed that y was x to the alpha, we threw that into our second order Euler equation, and we solved for which alphas would produce solutions. Now, when the quadratic formula that resulted produced two distinct real solutions, it was pretty direct to see that we had found two linearly independent solutions to the second order Euler equation. However, we were pretty vague about what to do when the two solutions are the same real number or a complex conjugate pair. We presented a fundamental set of solutions, but didn't really explain how we would find them to begin with. However, the other technique, which we will present shortly, more clearly goes over those possible scenarios. So let's go over how to make this substitution x equals e to the t. Now here's our second order Euler equation, just as it was before. If we assume x is e to the t, notice that this right away assumes that x must be positive. When we did the substitution y equals x to the alpha, depending on what alpha was, we may have had to make this assumption anyway. Here we just directly make it. If x is e to the t, it has to be positive anyway. Well, if x is e to the t, well then, what's dy dt? Because we want to go in terms of t, not x. Well, the chain rule says dy dt is dy dx dx dt, which means dy dx is the ratio dy dt dx dt, which is e to the minus t dy dt, because down here dx dt is just going to be e to the t. If I move it back into the numerator, it becomes e to the minus t. Therefore, axy prime is just a times dy dt. Here's dy dx, or y prime. It's e to the minus t dy dt. If I multiply this by x, it will cancel out the exponential, and I'll just have dy dt. So when we make the substitution x is e to the t, we found that the middle term of axy prime is a times dy dt. And just to be clear, the prime notation is referring to d by dx. So y prime means dy dx. But we're translating this into a problem regarding y and t and cutting x out altogether. So any primes refer to x derivatives. Now let's attack y double prime, or the second x derivative of y. Now the chain rule can apply again. If I want to find the t derivative of y prime, I can say it's the x derivative of y prime times dx dt. Now the x derivative of y prime is just the second derivative of y. So this is dy dx, and I take d by dx of that, and we get y double prime. But dx dt is just e to the t again. So what's y double prime? It's e to the minus t times dy dt. That's just taking dy prime dt on the left, e to the t y double prime on the right, and dividing e to the t over to this side. So we found that y double prime, and this is the second x derivative, is e to the minus t times d by dt of the first x derivative of y. Okay, so let's take that expression and see how does that interact with x squared. Okay, but remember that y prime we already know is e to the minus t dy dt. Therefore, y double prime is e to the minus t times dy prime dt. So I'm going to take d by dt of this expression right here. The product rule says, leave this alone, take d by dt of that. So we get e to the minus t and then the second t derivative of y, plus the derivative of this, which pulls out a minus sign thanks to the chain rule, times dy dt. Okay, now if I simplify this down, I can factor an e to the minus t out of these two terms, giving me e to the minus 2t outside the parentheses, and then inside we have the second t derivative of y minus the first t derivative of y. That's how we can substitute y double prime, the second x derivative of y. All right, so there's our expression for y double prime. And we've already determined what to do with ax y prime, so if I plug both of those in, x squared y double prime is e to the 2t y double prime, cancels out the e to the minus 2t in our expression for y double prime. Great, we found x squared y double prime is actually quite nice. It's simply d squared y dt squared minus dy dt. So now what we can do is we can take this expression for x squared y double prime, this expression for ax y prime, leave this alone. And now our second order Euler equation, by substituting x equals e to the t, is this right here. So here's the new form of our second order Euler equation, having successfully replaced all instances of the variable x with the variable t. If I collect this according to which derivative of y we've taken, we just have the second t derivative of y plus a constant times the first t derivative of y plus a constant times y equals 0. In other words, we have a homogeneous second-order linear equation with constant coefficients, and we know how to solve those. So now we consider the characteristic equation r squared plus a minus 1r plus b equals 0. But any solutions we get are going to be in terms of the variable t, not of the variable x. By performing this substitution, x equals e to the t, on the one hand, we got constant coefficients. Great, we know how to solve those. On the other hand, the variable will be t instead of x. All right, so having transformed our second order Euler equation into this constant coefficient equation, we generate a characteristic polynomial. If there are two distinct real roots, r1 and r2, we know that a fundamental set of solutions is given by e to the r1t and e to the r2t. But since x is e to the t, therefore t is the natural log of x. We don't need any absolute values or anything because we've already assumed x is positive. With t being log x, e to the r1t is just x to the r1, and e to the r2t is just x to the r2. That's exactly matching our other method of supposing that y is x to the alpha. When there were two distinct real roots to this quadratic right here, well then, x to those powers exactly form a fundamental set of solutions. But what if there aren't two distinct real roots? Well, we already know from our constant coefficient equation work that a fundamental set of solutions, if there's one repeated real root, is e to the rt and t e to the rt. Again, replacing t with log x, we get x to the r and log x, x to the r. This t right here becomes log x. So this explains where this other fundamental set of solutions, when we have a repeated real root, came from, x to the r and a log x, x to the r. And finally, what if our characteristic polynomial has complex conjugate roots? Well, if the complex conjugate roots are lambda plus or minus omega I, we know from our work with constant coefficient equations that the solutions would be e to the lambda t cosine omega t and e to the lambda t sine omega t. And all we have to do is replace t equals log x. With t equals log x, the e to the lambda t is just going to become x to the lambda, and the t's inside our trigonometric functions just become log x. So we end up with exactly what was proposed as a fundamental set of solutions before, x to the lambda cosine omega log x and x to the lambda sine omega log x. So having twice gone over why fundamental sets of solutions are given the way they are, let's put it into practice by finding all solutions to x squared y double prime plus 4xy prime minus 40y equals 0. Well, the characteristic equation you would eventually get after making the substitution x equals e to the t would become r squared plus 4 minus 1r minus 40 equals 0. Just remember that this isn't exactly a constant coefficient equation to begin with. You have to make this substitution to turn it into one. And the net effect is to subtract 1 from this middle term there. So we would end up with r squared plus 3r minus 40 equals 0. Factors very nicely as r plus 8 times r minus 5 has two distinct real roots of 5 and negative 8. So a fundamental set of solutions is given by x to the 5th and x to the minus 8th. Therefore, all solutions must be of the form y is some constant times x to the 5th plus some other constant times x to the negative 8th. I'd just like to caution you at this point, try to be very clear in your work about whether you are working with a constant coefficient equation or an Euler equation, because For a constant coefficient equation, if this just said y double prime plus 4y prime minus 40y equals 0, your characteristic equation would have been r squared plus 4r minus 40 equals 0, and your solutions would be exponentials. But the Euler equation is not quite the same thing, and after making the substitution x equals e to the t, you do end up with a constant coefficient equation, but a subtly different one. Instead of y double prime plus 4y prime minus 40y equals 0, you would end up with the second t derivative of y plus 3 times the first t derivative of y minus 40y would be 0, so the characteristic equation is slightly altered. This middle term gets a minus 1. Also, your solutions are now of the form e to the t to a power, which ends up being x to a power. Let's get more practice by finding all solutions to 2x squared y double prime minus 10xy prime plus 18y equals 0. The first thing we must observe is that we have this constant coefficient of 2 out in front of our x squared y double prime term, and we don't want it there. So let's divide that out to get the standard form. X squared y double prime minus 5xy prime plus 9y equals 0. Once we make the substitution of x equals e to the t, we will eventually get a constant coefficient equation. However, we have to subtract 1 from that middle term, so the characteristic equation would end up being r squared plus negative 5 minus 1 times r plus 9 equals 0. In other words, r squared minus 6r plus 9 equals 0. Factors very nicely as r minus 3 squared, but this only has a single root, 3, and it's a repeated root because we have r minus 3 squared. So a fundamental set of solutions is given not just by x to the third power, but also by x cubed times log x. So we found a fundamental set of solutions, x cubed and x cubed log x, which means all solutions are given by linear combinations of them, some constant times x cubed plus some other constant times x cubed log x. And let's do another example, finding all solutions to x squared y double prime minus 3y prime plus 5y equals 0. After we make the relevant substitution, the characteristic equation would be r squared plus negative 3 minus 1 times r plus 5 equals 0. In other words, r squared minus 4r plus 5 equals 0. However, this quadratic has no real roots. There are, however, two complex roots, 2 plus or minus I. So once we apply the quadratic formula here and find two complex roots, we know how to find a fundamental set of solutions. We let lambda be 2 and omega be 1, so we have lambda plus or minus omega times I, and we get a fundamental set of solutions as x to the lambda times the cosine of omega log x, and x to the lambda times the sine of omega log x. And with lambda being 2 and omega being 1, these simplify to x squared cosine log x, x squared sine of log x. Therefore, all solutions must be linear combinations of the two, some constant times the first plus some constant times the second. Overall, what have we done? X squared y double prime plus axy prime plus by equals 0 is called a homogeneous second order Euler equation. Second order because we have a second derivative, homogeneous because there's no forcing function, and an Euler equation is one in which these powers of x exactly match the number of derivatives taken in every term. Also observe that our highest order term doesn't have any other constant multiplying it. The way we solve it is to substitute x equals e to the t. After some work, this does result in a homogeneous second order equation with constant coefficients, and we know how to solve those. We take a characteristic equation. The resulting characteristic equation would be r squared plus a minus 1r plus b equals 0. And with our experience solving second order linear equations with constant coefficients, we know there are various possibilities. If there are two distinct roots, r1 and r2, then a fundamental set of solutions would generally be given by e to the t times r1 and e to the t times r2. But by translating this back to our original variable x, we would end up with x to the r1 and x to the r2. Similarly, if there's a repeated root r, we get a fundamental set of solutions x to the r and x to the r times log r. And if there are complex roots, lambda plus or minus omega I, a fundamental set of solutions is given by x to the lambda cosine omega log x and x to the lambda sine omega log x.